Hi guys, Zong here, back with another math video. 2 weeks ago, we did a question where we discussed that given an n number of cylinders, what was the shortest length of string needed to bind all those cylinders together. And if you don't know what I'm talking about, this is a problem I introduced 2 videos ago, and I suggest you watch that first. It introduces the problem. So without further ado, I'm going to go on to the solution of that problem, and I'm going to tell you guys right now there is no mathematical formula for the shortest length of string binding n cylinders. This happens a lot in mathematics where you have a certain problem that deals with a certain property of some set of objects like trees or something, and there's no set formula for solving that problem. So there's no formula for this problem, but I think it's important to actually calculate the shortest length of string binding any number of cylinders together. So let's think about it. Let's just go down the line here. So the first case obviously is just one cylinder. For each of these cylinders, we're going to have to make things easy, we're going to have our diameter equal to 1, right? Just to make things pretty straightforward. So we have one cylinder. Obviously, the shortest length of string to surround that is just going to be pi, because the circumference is just diameter times pi, so it's pi. What about for 2? So with 2, you have something like this, and when it's oriented like this, as you can see, you have two semi-circumferences right here, and you have two straight lengths of string that are equal to two radiuses. So each of these radii are 0.5, so they add up to 1. So this is 1, and this is 1. So the total length of string needed to completely encompass these two cylinders is 2 plus pi. And with 3, it's similar. Each of these straight lengths of string are 1. Each of this is 1/3 of the circumference, so it adds up to 1 circumference. So it's 3 plus pi. Let's think about something, because there's an interesting pattern that's actually going on here. We notice that each of the lengths of string has the term pi in it, so we begin to consider, is there going to be exactly 1 circumference for all of these cases? And actually, yes, there is, and we can actually prove this. So given any orientation of cylinders, if we want to bind it with string, we will always have 1 circumference as a term in there, and let's prove it. So consider this. Consider you just have the one cylinder and you want to bind it with string. Obviously this is going to be 1 circumference long. The string is going to be 1 circumference long. And why is that? Well, let's say the string first touches the cylinder like this, and the string is starting to wrap slowly around the cylinder. So right now the angle of theta is 0 degrees. Now let's slowly wrap the string around the cylinder so it's facing a different way. The angle now of the string is going to have turned. It's going to have turned a certain number of degrees. So let's say it's turned 60 degrees, right? And now it's facing this way. And actually, it's interesting because now that it's turned 60 degrees, the amount of the circle circumference that it's moved is also 60 degrees. And why is that? Well, if we're going to make this a bit bigger, we can actually prove that. So let's make a 60-degree angle right here, and I'm going to see whether or not this is 60 degrees. So let's think about this. So these are both right angles because they're tangents. So this is going to be 180 minus whatever this angle is. So this is just going to be 120, and this is going to be 180 minus whatever this angle is. So these two angles are the same. So when this string moves, turns a certain number of degrees, it also takes up the number of degrees of its circumference as well. So when we completely wrap this cylinder, the string will have turned a total of 360 degrees. it'll be here, and then it'll be here, and then it'll be here. It will have turned a total of 360 degrees, and it will also encompass 360 degrees of the circumference. And so when you have a bunch of circles bound together, we know right off the bat that this is going to turn like this. It's going to turn again here, and it's going to turn again here, and it's going to end up where it originally was. So it's turned to complete. The string itself has turned 360 degrees, and so the amount of circumference that it has covered must also be 360 degrees. These angles must all add up to 360 degrees, because for every angle the string turns, that angle is the same as the amount of circumference that it covers. So, thus every possible case will actually have a pi term in it, because in every case the string is gonna cover exactly one circumference. So next we're gonna keep going on. We're gonna go with 4, and we're just going to. So where would I place this? Well, no matter where I place this, it's blatantly obvious that the shortest distance of string I can get to cover 4 cylinders is like if I place it right here. Because if I place it right here, it's going to be really long, and you know, if you've ever tried to like push a bunch of soda cans together, you know that this is going to be the shortest. And I'll discuss why later. Actually, we're gonna discuss how we know each orientation is going to be the shortest orientation possible. So let's think about this. 4, it's pretty straightforward. There's going to be a pi term, and then there's 4 straight segments, so it's going to be 4 plus pi. With 5, it's also pretty straightforward. You're going to just have this, so it's 5 plus pi. And then with 6, it's different. With 6, you sort of have to consider what to do next, because we could have it like this. It's not so blatantly obvious anymore. We could have it like this, or you could have it like this, which is shorter. Let's think about that. Actually, let's think about this. So if we place it here, we're going to be adding 2 straight line segments. So instead of using, we're going to be adding essentially a complete straight line segment. How do I know this? Well, if we take away this segment of the string, we're basically replacing it with 2 straight line segments. So that's going to be adding 2. But if we place the cylinder here, we're going to be taking away 2 straight line segments and adding one that is not quite 2 straight line segments. So that would be minus 2 plus 1 plus something that is larger than 1. And what is the length of this, actually? Let's calculate that. So the angle that these circles make is 120 degrees, intuitively, trivially. And by law of cosines, we know that the length of the third side is equal to the square root of a squared plus b squared minus 2ab cosine theta. I think that's right. And cosine theta is, a cosine of 120 is negative 1/2, so it actually just becomes a squared plus b squared plus ab. So if these two lengths are 1, then the length of this third side is actually square root 3. And this is parallel, so the length of this domain is going to be square root 3. So it's going to be minus 2 plus 1 plus square root 3. So the length of the entire thing actually doesn't increase that much as adding the cylinder here, where it increases by 2. Okay, so so we know that placing the cylinder here is actually good. It's better than placing it here, and it's sort of intuitive actually, because if you have a certain area, in this case cylinders, that you need to, if you have an area of cylinders and you want to find the shortest perimeter, well, you want that a circle's going to have the shortest perimeter for a given area. So you want to make sure like the cans sort of form like a circle. Like if you have a ton of cans, like 1,000 cans, you don't want them to form a long line of cans. You want them to form sort of like a circle-like shape. So it makes sense that, yes, and I'm going to sort of reveal the secret now. It makes sense that we're sort of moving these cans in a circle when we place them. And by doing so, well, we're ensuring that the overall shape is a circle. And this is actually the shortest way you can actually bunch these cans together. So for 6, I think it's going to be 4 plus square root 3 plus pi. And for 7, it's going to be 7 is special because it's I'll tell you why. This question contains a lot of interesting math concepts. Anyway, 7 is actually 6 plus pi. So the pattern sort of broke down. We went from 0 to 2 to 3 to 4 to 5 to 4 plus square root 3 plus 6 plus pi, which is one of the reasons why there's no set mathematical formula for doing something like this. But let's see if we can't really derive some sort of method or technique for solving this. So let's just keep going. So for 7, and we add another one, so that becomes 8. And all of these are straight line segments, pretty straightforward, so that would be 7 plus pi. And for 9, it's actually weirder. So for 9, it gets a bit more complicated, because we added one here. Why not add one here, or here, or here? Remember if you remember when I said that we want to add these in a circle-like fashion, but this shape just looks sort of awkward. Like there's just a thing sticking out there, and there's like sort of a gap there. That's sort of awkward. Like, wouldn't it be better to place it here? Let's do the same sort of analysis. If we place it here, we're gonna take away a straight line segment, and we're gonna add 2. So we're gonna that's going to be adding one total length to the entire perimeter. Let's say what if we add it here though? Well, we're going to be taking away these 2, so it's minus 2 plus 1 plus square root 3, like we calculated before, which is going to be square root 3 minus 1. That's actually smaller than 1, because 1 is equal to square root 4 minus 1, so square root 3 minus 1 is going to be smaller than that. So actually that's still the shortest, even though it doesn't really look like it, and it looks sort of weird. But yeah, it's sort of further proof that in order to keep the shortest string to bind these cans, you want the cans to sort of go around like this. Okay, we got that. So if we keep going and yada yada yada, we sort of see this pattern emerging. There are certain, I should say, landmark. If you want, let's say someone just asked you, you have n number of cans, and I want to find the shortest length of string to do this, and you want to just solve the question the fastest way possible, which is incredibly hard when there's no formula. So there are actually these landmark numbers that are really useful for you to approach this problem. So let's think about this. So the landmark numbers are 1, 7, because 7 forms like a complete nice circle. The next one is going to be if you surrounded 7 with circles, and that's actually, if I remember correctly, that's going to be 19. Yes, 19, I think, is the next one, where you just surround 7 with these circles, and then you have and then the next one's going to be 37. These are landmark numbers. So 1, 7, 19, 37, and so on. And actually, these numbers are pretty cool, because the formula to derive these numbers is 3n squared minus 3n plus 1. That's a really weird quadratic formula for finding these landmark numbers where the cylinders all form like a hexagon. And I'll probably go over this in another video sometime later, because this will actually take a bit of time to prove. But this is how you find those landmark numbers. So let's think about something else. Let's think about what the shortest length of string is going to be for those landmark numbers. And actually, there are going to be multiples of 6. And how do we know this? For 1, it's just pi, right? But for 7, you have 6 sides, and these 6 sides each have a side length of 1, right? So the whole number part of the string length is actually just going to be 6 plus pi. For 19, it's going to be something. I should just draw it out for to help you guys just visualize this. Okay, each of these sides is going to be 2, and there's 6 sides, so it's actually going to for 19, it's actually going to be 12 plus pi. So actually, they just go up by multiples of pi. So we notice that if we plug in 1 to this equation, we get a circumference of length 0. And if we plug in 2 to this equation, we get 7, and the length of each side is 1. So if we plug in 3 to this equation, we get a side length that is 2, because you get 19 out of that. So if we plug in 3 to this equation, we plug in 4 to this equation, we get 37. So intuitively, that side length is going to be 3. It's just 1 minus whatever number you plugged in to get this number. So we know that for 37, it's going to be 18 plus pi. Now it's where it gets a bit interesting, because when you start adding on, these spheres, you want to see if there are any interesting properties that happen after you start adding on spheres to these hexagons. And well, let's just see. So we're going to actually go off. I'm going to try to use. Alright, give me a second. I want to try to use this diagram. I don't really want to redraw all these circles, so we're going to use some magic of paint tool psi. Hopefully I can. Why is it not letting me do that? Okay. Please. Okay, there we go. Okay. Let's start adding on spheres. So now we have 38. Now we have 38, 39, 40. That's weird. What is the length of this thing? The length of this thing, as we discussed before, is just going to be a squared plus b squared plus ab. The length of this is 1, the length of this is 2, so it's actually going to be square root 7, so this is square root 7. That's 40, right? So with you could then add up all these integer lengths and then calculate this thing. And then with if you add another one, this becomes square root 3. And if you go even higher, like to even higher numbers, pretend this is all filled up, then you get stuff like this, where this thing becomes even larger, and I think that becomes like 3 squared plus 3 plus 1, which is 9, square root 13. It's square root 13, and then it becomes square root 7, and then it becomes square root 1 as you add more circles, square root 3 as you add more circles. I think you can use this formula to skip to a certain number of cylinders you need, and then from there you can start sort of filling in the circles and counting up the integer side lengths. That was a long problem. It's hard to explain. It's hard to grasp. It's sort of hard. I think it comes in contact with a lot of interesting mathematical concepts like law of cosines, and this random combining geometry with algebra. Like, how do you know how do you know if pi shows up in everything? How do you know if that's the smallest length? Yeah, I like this question, even though it doesn't have a pretty solution. I'll see you guys next week.